Good afternoon. I hope that everyone has enjoyed the lunch and that everyone is ready for the third part of this session on monitoring and measuring. We are going to have 4 speakers and then a break of 30 minutes and then another session with 4 speakers. I would Conroy comes to deliver his talk. It's about Dutch peatland subsidence observation using InSAR. And this afternoon, we will have more about monitoring of peat. Yeah, thank you. Yeah, I'll take this. Yes, so you just have to keep this on. May I?
Yeah, please do.
Well, yes. And then this one too.
Okay. Hello, can you hear me? Yes. Great. Hi, everyone. So my name is Philip. So I'm going to be talking about trying to use InSAR to monitor the subsidence of the Dutch peatlands. So if you're here for the sessions in the morning, you saw this map with green and red dots that were sort of subsiding, especially around the Groningen area. We saw a big red blob around there. Another thing you might have noticed in that map was that there was a lot of gaps in it. And that's basically because that map is generated using point scatterers. And so that basically equates to using the reflections of buildings in the built environment to assess subsidence. But that doesn't really tell us anything about, can I use this? Is this a laser pointer? No, it's a slide thing. That doesn't really tell us anything about the fields themselves. And so we did hear about, that a bit as well this morning. And really, it's a big unknown here how much these fields are really subsiding and how much they're really moving. So it's important that we try to develop a methodology that allows us to use InSAR over these areas as well. So here you see in this picture a typical parcel of land in the Netherlands. And you can see there's a sort of cross-section that you can imagine. And the top of it is sort of, some kind of a crop or grassland that's very typical. And then you have a sort of section that lies above the groundwater level that is sort of, I called it dry here, but that's not the technical term. But of course, this moves up and down throughout the year. And this, and then below that, we have the groundwater. So this gives us a lot of challenges when we try to monitor it. So first of all, we have large fluctuations in the land cover if there's mowing or harvesting going on. We have large fluctuations in the water table, both natural and artificial, caused by pumping, and very rapid surface movement. And so this rapid movement of the ground, along with changing noise levels throughout the year, and phase unwrapping errors for the InSAR people, it makes very difficult to actually monitor this area. So here is an extensometer measurement to give you a sort of an example of what we're looking at. I should acknowledge the colleagues from the NOBV project who provide this data for us. It's been instrumental in our work. And here you can see this is a sort of typical area called Zegveld that I think some of you might be visiting tomorrow. So this is a time series of a certain point measured by an extensometer. And to give you an idea of sort of what we're looking at here. So we have very strong deformation rates, especially in the fall. This is on the order of, up to 30 centimeters within a few weeks. And so this can actually exceed the ambiguity threshold if you're trying to unwrap a phase time series using InSAR. So you're essentially guaranteed to have phase unwrapping errors if you just naively unwrap the time series. We have very high range, throughout the year. You can get here around 8 centimeters. It can go up to like 10 centimeters throughout the year. And then the main one that I'm going to be talking about today is we have basically a complete loss of signal in the summer. And that's due to basically agricultural activities, differences in the weather and so on. And everything kind of adds up together to really have very high noise levels in the summer, and we can't do much with the measurements that we get there. So to give you another idea of what we're looking at, so this is a sort of typical radar backscatter image. So you can see this is sort of like a picture of the area. And then when we do interferometry with that, we actually combine multiple images together to track the changes over time. So this is sort of the backscattered power, but in interferometry we look at the other part of the image, which is the phase. And here we can see sort of differences in that phase over time. And just to give you an idea, I was hoping I had a laser pointer. I can't really point it out to you, but you can kind of see this. Okay, very nice. Okay, so you can kind of make out some similarities to the previous slide, right? But you can also see that this is extremely noisy here, and so we have to try and average this together and get some kind of measurement that makes sense out of it. This is the most technical slide of the whole thing, so please just bear with me. So what this shows us is basically every combination of images that we can make. And what you can see is that this is the basically the correlation between those images, between those pairs of images that we can make. The takeaway message basically from this picture is that in the summer, there's very, very little correlation, which means that there's very little signal for us to track. Actually, there's basically zero. There's nothing here. And so what we have is basically not a continuous time series, but something that's been essentially broken apart. And there's nothing here that sort of connects the two coherent periods together. And just to give you sort of an idea. So what we do is we average a certain section of land together, and then we can use that to estimate the coherence for one certain interferogram. So for these dates that we're looking at here, this very noisy thing is actually still in our sort of relatively speaking good period of time. So just to give you an idea of the challenges that we're dealing with here. This is sort of a very similar image, just shown differently. Here we sort of more explicitly state sort of these are the periods that we can use. Whereas here in the summer, we don't really find we have enough consecutive images to have a useful sort of time series. So our first approach is just to take the data that we can use and treat those segments as their sort of own individual time series. And that gives us, a partial sort of fragmented story of what's going on. And that's great. But that only gets you so far. Right? So here, for instance, we have two segments that we, for now, assume are sort of interpreted correctly, unwrapped correctly, but they're disconnected, and we don't know where they are in relation to one another. So you can say there's a sort of unknown shift between them, and that shift represents the unknown displacement history that took place during this period that we couldn't, I lost my thing. During this period here that we couldn't measure anything. So how do we reconnect these segments? How do we get a story that goes from beginning to end here? Now I'm just going to take a step back and show you sort of we bring other additional information into it to sort of try and fill in these gaps. So I'll show you, try to walk you through the process of what we do. So here you can see basically, okay, it stopped working again, but you can see a map of all the parcels in a certain region here. And what we can do is we can attribute data to these parcels. For instance, their soil type, their land cover, what kind of agriculture is being done there, and their groundwater management. In Dutch, that's called the peilgebied. And basically, this is a zone in which the groundwater is held within that zone at a constant level. And so what we can do here is sort of make combinations of different areas together and try and maximize the amount of space and spatial measurements that we take together to sort of lower the noise that we have. So this is a game you have to play of sort of try to get as much noise suppression as possible while still maintaining a representative measurement. So here you can see essentially for every parcel in this group that I've identified that we expect all of these parcels to behave in the same way because they have sort of the same contextual data. But you can see that they actually have, oh, oops, sorry, I went back. I went too far there. So here you can basically see when there's a line here, we have basically a signal that we can work with. We have coherent data, and when there's a gap, we find we have incoherent data. So when you group enough of these parcels together, you find that actually there is enough data there to sort of span this incoherent period, and you can fill in the gaps. So now I can go back to those segments that I showed you earlier, and if we just plot them all together, all of them starting at 0 with some kind of unknown shift between them, you see it's a mess. It's basically like a spaghetti with the Swedish chef. And so we need to be able to reposition all of these segments with respect to each other in the way that makes sense. And the way we do that is we look at the change in position over time. So basically we take the first derivative, and in that case, any kind of vertical shift will just drop out of the equation. And that allows us to then parameterize a model, estimate where these segments should be in the mean sense. And so when we do that, you can sort of add here I've shown a very simple model that you could use. We can shift everything together, and now you can see everything has sort of spread. It was very spread apart. Now it's very close together. And this is just, in this case, just a sinusoid, just to give you the example that really you can use a very simple model and still get a result out of this. In the future, of course, we can add more sophisticated models that are based off of the hydrology of the area, for example. But here we're just showing you sort of a toy example, basically, that the simplest model you can think of can give you actually a very good result already. And so this is, when we glue it all back together and we get something, this is sort of the final time series that we get. This is what it looks like. And so you can see for that one group, we have basically one mean displacement that you can see in blue. And you can see that that actually correlates quite well with the point measurement from the extensometer that we have in the same area. So we shouldn't expect them to match 1-to-1 because, you know, this is the InSAR measurement here is a very large spatial average. So there will be differences between that and just the point measurement. But we're happy to see that the same general trends exist. And in the short-term sense, is this thing working again? Yeah. You can see they do sort of respond to the same stimuli. In particular, one thing that's interesting to note is in 2018, we had, I think, one of the hottest summers on record. And you can see here a very sharp decrease. And there was sort of a much more permanent effect caused by this summer compared to, say, other ones. Yeah, and then in gray, you can see, in gray, I've just plotted all the individual segments. But if you give them color, it becomes very difficult to kind of interpret. So I've just shown it here to give you a sort of a sense of the dispersion that we see within a given group. So yeah, to conclude, basically the story is that we have this sort of loss of signal that we call a loss of lock. And this cuts our InSAR time series into these disconnected segments. We can find neighboring points, we identify them using contextual data, and we can use those to fill in the gaps in the incoherent segments. And this has allowed us to get the first sort of accurate time series of surface motion in the Netherlands. So we're very happy about that. In the future, we want to implement more sophisticated models to perform this segment realignment. And finally, we'd like to do a more quality assessment on it to make sure that the model is actually valid, that we fit to the data. So yeah, thanks very much.
Yep, thank you for your presentation. Nice to present novel processing of InSAR data. I'm sure there are questions. Yes, I'm coming.
Yes, thank you for interesting presentation. My question is actually, what percentage of the agricultural fields in the Netherlands do you expect that can be monitored with this way?
Well, I guess ideally all of them, right? Right now I've restricted myself to grasslands because I think once you have, for instance, maize or something like that, you have different processes going on like harvesting and plowing. I think in principle, there's no reason why we shouldn't be able to deal with those as well. But for now, I've just restricted myself to the grassland, which is, at least in the areas that I'm looking at, I would say around 90% of the fields. I think if you go north to Groningen, it's a bit different. I think there's more there, but in the south, it's almost all grassland. Yeah.
Yes, another question?
This is a very interesting talk. Can you comment out on the spatial resolution of your final these pounds? That's called DS or whatever pounds. And what's the implication if you have very heterogeneous settlements on the peatland?
Yeah, thanks for that question. So we've done something that's a bit unorthodox in terms of spatial resolution. And what we do is we actually use these parcel delineations as our multi-looking boundary. So instead of just taking a square and applying some kind of a statistical test to see what pixels sort of behave the same way, we use the boundaries of the fields themselves given from this data sets to do the multi-looking. And so that means that every field will actually be slightly different size and shape. On average, I would say that you have about, I would think there's about 100 pixels, roughly, give or take, within one of these parcels. But you can see that it's sort of the shapes vary. That being said, that's just for one parcel, right? To get a full time series that spans the whole thing, you need a group of parcels. And so in this case, I think I had about 50 of them. And so here you see this is approaching about 1 kilometer in size now to really get a full time series. If you're happy with a partial time series, where it's only during those coherent times that I identified, then we can have a higher resolution again. But for a totally unbroken time series, then you need to go to this group scale.
Thank you. Another question? Yeah.
Well, first, congratulations for your presentation. Just one question. As I see, when you are like an averaging some different points to get a better signal, and you take advantage of the land cover maps or something like this. My question is, how do you integrate all this information to the InSAR, let's say, chain, processing chain? I mean, it's a manual task that you have, or how you ponderate which weight you give to every different layer of information.
Yeah. So what we have is essentially you have a coordinate. You can do some geocoding of your SAR pixels, right? And then I think in the Netherlands, we're quite fortunate to have a lot of land covered data, like land use data. But all of this is basically freely available data, and you can download it, and it's very simple to integrate because it's all given in sort of these geopackage formats, right? So the integration step is quite simple because then you can basically use the latitude, longitude coordinates that you've estimated from your SAR processor and assign them to different groups. So I've had to create this system myself, but it is actually quite easy to implement, I would say. Yeah.
Would you consider using HN data to maybe reject some anomalous points through some parcels? You know, the map elevation?
Yeah. That's a good point. I think so, because also the AHN gives you an indication of the history of the location, right? If it's very low lying.
Maybe you could see some channels, shallow channels having another kind of subsidence than the rest.
Yeah, so I would say basically the whole methodology, there's areas that we can,
You can
improve things. But for now, I've just focused on basically the land cover and the Peilgebied
It's
to
already very good.
simplify the task, yeah.
Another question, maybe? No? Then thank you very much for your talk.
Thanks.